In this video, we're going to talk about mass and center of mass of rods. Now, things that look rod-like. So this is a 20 centimeter piece of wood, and the density of this, linear density, is about 0.22 grams per centimeter, which is to say that if I take 1 centimeter of length of this rod, it's about 0.22 grams. Now, if I take the whole length of this rod, this is a 20 centimeter rod. Let's see, I think it should be 20 centimeters times 0.22 grams. It should be about 4.4 grams. Let's go find out if that's really the case. .3 grams. Pretty close to 4.4 grams. Good. Okay. We can write this as an integral as well. While for a straight rod like this, that's not really too enlightening, it turns out to be useful for other shaped rods as well. The 20 centimeter rod then, at 0.22 grams per centimeter, turns out to be about 4.4 grams. You can see that by 20 centimeters times 0.22 grams per centimeter. And that gives you 4.4 grams. Pretty close to the measured value of 4.3. It's pretty close. Now, what about this another sort of more funny shaped rod? One that, if I were to plot it, its density delta, that's the Greek letter delta. Its density is constant on one side of the origin, and on the other side it increases linearly. Let's still make it 20 centimeters, so from minus 10 to 10 on the x-axis, reading out in centimeters. We'll make this 0.22 grams per centimeter density, and this side here, it will increase linearly. And the way I'll do that is just simply with the equation of a line. And in fact, if you look at this, you'll see that if I put x equals 0 into this expression for the density, for x greater than 0, if I put x equals 0 into there, I'll get 0.22 grams per centimeter, just as giving you this matchup right here. Just as you should. And if I put in x equals 5, or rather x equals 10, you'll find that I'll get 0.22 times 5. So this point here is 5 times the density as down here. And actually, a really easy way to make this kind of rod is just to make a little thin plate that looks just like this. Okay, so what's the mass of this? What's the mass of this rod? Well, the way that you could find the mass is by integrating the density. So let's integrate from 0 to 10 of the density. And this is still the Greek letter delta. Looks a little bit like an H or maybe an S, but it's a little delta, lowercase delta. It's a piecewise continuous function, so let's split it up into two segments, to the left and to the right of the origin. On the left, the density is just constant at 0.2 grams per centimeter. So it's just constant. On the right is 0.22 grams per centimeter, but it varies with this expression. Okay, that latter integral presents no problems. I'm leaving off the units just to save time in writing, but you definitely don't want to forget the units. And substitute in the values for x. If you do this, you should get a value of about 8.8 grams. Let's see how that checks out. Okay, so I have a rod, so to speak, that is about the same shape as we just looked at. And we claimed that the mass of this should be about 8.8 grams, 8.5 grams. Not too bad. So the math seems to work. Now what about the center of mass? That's the balance point. Well, for a uniform straight rod like this, I think you probably can guess, if I hang it from the middle, it'll just balance. And indeed, you'd be right. It balances just fine right from the middle. But what about this other rod that we were looking at? This rod that's got some non-uniform density. Where should it balance? Well, if I do a little bit of trial and error, balance is right here. Now that is about 3 and a little bit centimeters off of the center. But we can compute what that is using the mass integral we already have and another integral called the moment integral. Now, given that we found the mass already of this funny shaped rod is 8.8 grams, we're going to use that information when we find the center of mass. The center of mass is actually found by way of two integrals. Sometimes we'll call it x bar, or sometimes we'll call it the centroid in x. All of those are the same thing. And the way that we find it is by way of a ratio of two integrals. We've got the mass integral that we already had. So that's the mass integral. And we have what's called the moment integral. And the moment integral looks very much like the mass integral, except that it's got an extra x. So for this funny shaped rod, we already know the mass is 8.8 grams. With the moment integral, we need to compute. So let's compute that. So as before, we'll want to split this up into two pieces, a piece on the left of the axis and a piece on the right. The piece on the left, it's no longer a constant, although the density is constant. And I'll leave the units off. The one on the right has the same density out front and the same change in the density, same density formula, but now it's got an extra x. Okay. As before, neither of these integrals are particularly difficult to do. Let me just take the 0.22 out and we'll bring it in at the end. First integral is easy enough. The second integral is also not so bad. Okay. And putting all the pieces together here, one thing to watch out for is your signs. So this is 0 minus 1/2 x 10 squared. That's 100. And then this one comes in with a plus. Okay. Before we write down the answer, one thing to notice is that this cancellation here This cancellation is actually what happens in the uniform rod. It's because our rod has got a part of the uniform rod already built into it. If I look at it here, here's the rod. It's already got that uniform rod that's got a center of mass being right at the origin, right here. So what the integral has essentially done is it's split the problem up into these rectangle and triangle problems, and it's having you solve them separately. But you didn't need to know that. I'm just showing that to you so you could see some of the things that that integral does. Okay, going back to computation, let us punch this into handy-dandy calculator. And we get the figure 29.3, and that's the moment integral. Okay. What are the units on that? The units are actually kind of strange. The units on that are centimeters grams, or gram centimeters. They're actually units of what's called torque. It's kind of like a force, but for twisting. Okay, in any case, the center of mass formula says I need to take the moment integral, which I just found to be 29.3, and divide it by the mass integral, 8.8. Okay, so our center of mass then is 29.3 gram centimeters divided by 8.8 grams. And if I put those into my calculator, I find a figure of 3.3 centimeters. Now, what does that mean? Well, that's an x coordinate, and it says that the center of mass is, there's the center of mass is along this line, which is 3.3 centimeters from the center. And indeed, that's exactly where I showed you with the actual thin rod, in quotes, it's more of a plate. That's right where it balances. So this center of mass formula checks out and works perfectly fine.